Cool. So to give you a little bit of an overview for what's coming, this lecture is actually going to be in 2 parts. And so I'm first going to tell you about this question that I've put up on the board here. So trying to quantify why it is that simple models are better. One way to think about the last lecture I gave and part of what Mark's been talking about is that in many cases you can get by with a simpler model, so you don't need as complicated a model. And here I'm actually going to try and convince you that in many ways a simpler model is quantifiably better. That I think will take about the first hour, and if it runs over that, I can move some of the rest of it to tomorrow. But the second half of the lecture, or the last third, I want to talk about the Jarzynski equality and the fluctuation dissipation theorem, and this will be building up to the geometric framework for understanding dissipation that I'm going to be telling you about tomorrow. So this will be a bit of a detour from information geometry, but we'll come back to that tomorrow as well. So actually I want to ask you guys this first. So any thoughts as to why a simple model would actually be better? Sorry? Easier to calculate, and I would put this generally under the grounds of aesthetics, right? That you want a model that you can look at and understand and that you can run on your computer without a lot of work. Aesthetics. Another common thing so I'm actually quite partial to this. I'm going to be telling you something else, but I'm not convinced that this isn't really why we prefer simpler models. Another thing that's commonly used is overfitting, right? So if you have a more complicated model, you have to worry about overfitting. And I'm actually less susceptible to this, so I think this is a real problem if you're doing curve fitting. But one of the things I'd like you to keep in mind here is that if you have a model that has this hyperribbon structure that we've been talking about, I would argue you don't really need to worry about overfitting, that these extra parameters that you have in your model, in general, or in the most common case, don't give you any more flexibility to fit your data. So I'm less susceptible to this one. But today what I'm going to be trying to argue is that, and I want to also stress that this is different from overfitting, that a simpler model can be quantifiably less biasing. And I'm going to try and tell you what I mean by this and how to quantify it. And to give a little outline for the first half of this talk, I'm first going to give sort of an introduction to priors and what's meant by a prior. And Florent gave a little bit of this in his lecture, but I'm going to go into a little bit more detail. Then I'm going to show you how a flat prior, which I think is probably the naive choice of a prior, is sick. And I'm going to show this with our favorite model, the sum of exponentials. Then I'm going to tell you about the sort of broad theme of an uninformative prior. So the idea is to choose a prior which doesn't presume anything about the data that's going to come, or presumes as little as possible. That's why it's called uninformative. And this thinking is traceable to Jaynes and Jeffreys, I think in the 50s, though I guess I wouldn't swear by that. Then I'm going to tell you about Jeffreys' prior. So this is what Jeffreys thought the right unbiasing, uninformative prior would be. And I'm going to show you that this has a very nice interpretation in terms of information geometry. And then I'm going to try and motivate Jeffreys' prior a little bit more quantitatively with the idea of reference priors, which are traced to Bernardo. And then I'm going to argue that for typical models that are hyperribbons, Jeffreys' prior is actually also sick. And instead, we want to really take this reference prior seriously and take the small m limit. And I'll tell you what I mean by that. And this is sort of preliminary work that I'm doing with Mark Henry Mattingly, who's a grad student at Princeton, and Michael Abbott, who some of you may have met last year, who's in string theory in Poland at the moment. Okay. So I want to think about some general data x. And it's going to be helpful to, x is already a vector, but it's going to be helpful to think about data that's repeated from the same experiment that's repeated many times. Where each of these are vectors. So in the case of a summing exponential with 2 data points, m is not 2, m is the number of times I repeat exactly the same experiment. And we're going to think about a model. So our model has some parameters theta, and it makes a prediction or a probability distribution on the space of data, like we've been talking about before. And what we're going to try and do here is invert this. So this is sort of input to the problem. But what we want instead is probability of theta given x. And I guess probably most people are familiar with this, but I want to go over it once just to be sure. The key point in doing all this is mathematics, and that's Bayes' theorem. So we can write the joint probability distribution of x and theta in 2 different ways. We can either write it as p of theta times p of x given theta, or we could have written it as p of x times p of theta given x. Do we agree that these should really be equivalent? They both give the joint probability distribution of p of x and theta. And as a result, we can write p of theta given x, p of x given theta, times p of theta divided by p of x, actually. Yeah. So this is Bayes' rule. You're not allowed to argue with this. This is the posterior. This is the likelihood. This here is the prior. And this I learned in Florent's lecture is the evidence. And it's really just a normalization, right? Because once you have data, this happened, and so it just drops out. This is just mathematics, right? This is clearly true, and I've just rearranged the terms. But you are allowed to argue that this is sort of a silly thing to do. So if I really believe that my model is correct, this p of theta is not really a probability distribution, right? So if I have an experiment and I have a Geiger counter, so this is the experiment I'm going to be talking about, and I'm trying to understand what these thetas is, presumably p of theta is a delta function somewhere, and I just don't know where it is. And so this is kind of a strange thing to do, right? This is, in some sense, quantifying how little you know about the problem, and whether you're really allowed to treat that like a probability distribution and use equations like this. This is sort of the controversy, right? Yeah. Yes. Exactly. Yes. So X would be a single experiment, and eventually I'm going to talk about just repeating the same one. Yeah.
It'd be a single experiment where it takes multiple.
Exactly. And it turns out this is a convenient way to taking the M large limit makes lots of things simpler. And now that I've said that, one of the things I'm going to try to argue is that that's not really the right limit to think about these sloppy models. No, so each of these might have several data points in it. So each x here is the same exact experiment over and over again. So these are already a vector. Yeah. So maybe it will make more sense actually when I draw the first example. But so just there's various things you can do in data fitting. So one is to just maximize the likelihood. That's maximum likelihood estimation. Another thing you can do is try and maximize the posterior. This requires this prior, right? But here I want to consider the ensemble of p of theta given x. So I want to be able to say, if you give me some x, I want to be able to give you an ensemble of p of theta given that x. So here, our goal is not to find the maximum likelihood estimate, but to find an ensemble of parameters given some data. And I want the whole probability distribution or a whole ensemble that's reasonable. This is all well defined except for the choice of p of theta, right? So the question that we're going to be addressing for the rest of today is how do we choose the prior? Okay, so I'm going to start with the same model that we've now studied to death. So y of t e to the minus k2t, so sum of two exponentials. Theta here is just k1, k2. As we did before, the probability of getting particular data x is going to be given by p of xi over 2 sigma squared. Very much. Yes. Wrong here. Okay, and let me actually just first draw what this is going to look like. So we've seen it many times. And I'm just going to be thinking about this at 2 data points. X is going to be x1, x2. I'm going to have some data like this. Here's 1 here. Here's t here. Here's y of t here. And just so that it's up here, here's y of the maximum likelihood estimate. Something like this. So the way I've drawn it, or maybe it's hard to see from the way I've drawn it, it's impossible to go through the center of both of these. So the maximum likelihood estimate is not perfect, even though I have 2 parameters and only 2 data points. But we'll talk about that more. The other thing I can draw is my parameter space. So here's K1, and here's K2. And just so that there's no confusion about symmetry, which I don't want to be talking about, I want to specify that K1 is greater than K2. So my allowed models live somewhere in this lower triangle here. And the first thing I want to do is convince you that a flat prior is not reasonable. So I want to go way out like this and put k max here. I certainly need to define a bounding region if I'm going to have a flat prior. Otherwise, I can't normalize my prior, right? and my flat prior, so flat in K1, K2, this is going to look like something like this. Right? Just uniform in the space. And in fact, it goes all the way out to here, right? And so when I plot that in here, when I map this parameter space back to the actual plots that I'm making here, this is actually going to be very distorted, right? So this, if I choose a prior which is uniform here, so flat P of theta, I'm going to be dominated by the very large k values here out to the value of k max, right? So when I draw that, typical models from this are way out here, right? Where this width here is something like 1 over k max. So I think you'd agree this is very biasing, right? And in particular, if I think about the models that are way out here, they actually have finite cost, right? So they have a finite likelihood, right? So if I take one of these models, it's maybe a few standard deviations away from the data, but that's finite. And so as I take my k max to infinity, this is p of theta, but p of x given theta is actually the same, right? Does this make sense? So because even way out here, I'm fitting my data with finite cost or with finite likelihood, when I actually fit to the data, I don't really change this distribution. And this is called parameter evaporation, right? It's sort of analogous to two hydrogen atoms if I really have infinite space, their ground state will not be bound together because there's infinite space and they'll be separated. Okay. To really stress how strange this is, I want to write down what I claim is really an equivalent model. So I could have also written y of t as 1/2 e to the minus t over tau 1 plus e to the minus t over tau 2. And I think you'd agree that this is an analogous model. Yeah? But it makes a totally different prediction if we use a flat prior, right? So flat in tau 1, tau 2. What's this going to look like? Oops, I've used this color. So this is all going to be concentrated down here, right? So now I'm going to be dominated by very large taus. And those are going to sit somewhere here, where this is 1 over tau max. And so these models are all going to sit up. And so this is also going to be quite distorting, right? And again, this model here does fit the data with finite likelihood, right? So it's not that as I take tau to infinity, I can reject that model because it fits the data infinitely badly, even though the parameters are bad. Okay? I want to draw one more plot, which is y of t1 and y of t2. And as we discussed before, not all possible values are fittable here. So here's 1, here's 1. And as we discussed before, this plot looks something like this. So let me just label a few things here. This is the line where K1 equals K2. Here's the line where K2 equals 0. Here's the line where K1 equals infinity. And all of these possible models can fit somewhere here, but let me just draw where two of these distributions are. So the green distribution, this is dominated by K1 and K2 being close to infinity, right? So that's going to sit somewhere down here. If I look at the orange model, that's going to be somewhere over here. The way I've drawn my data, the first data point is higher than is possible to fit, and the second point is lower. Right, so my data is sitting somewhere here. And what that means is that my best fit, which is just the closest point on this model to the data, is actually sitting at one of these boundaries, right? So if I use the purple dot, my best fit is somewhere there, right? So even though I have this two-parameter model, the best fit doesn't know about it, right? It's just sitting on this one-dimensional subset of the possible parameters. Okay. I don't know. Is it bad? It's strange, right? So I would say that this argues against overfitting, right? So this is almost the opposite of overfitting. So I allowed the model to have two parameters, and I made the best fit, and the best fit is where you'd worry about overfitting, right? But even though even though I allowed it to choose the model which best fits the data, it chose a one-parameter subset of my two-parameter model. So as Mark was showing yesterday, as T1 and T2 get close to each other, this is going to get very narrow, and so typical data will actually push you to one of these one-parameter models. Yeah. Yeah.
Is there anything sort of deep there? Couldn't I take the most priors and make the coordinate change and have the coordinate change? And then if I look back in the original coordinate, just to that prior, I could just make it look sick.
Yeah, so it is certainly true that a flat prior in any coordinate system will look sick in some other coordinate system. And I actually think this is a good motivation for what we're going to be talking about next, which is uninformative priors. So I think this nicely motivates the problem of choosing the prior, right? So I think these are the two naive choices, and they're certainly biasing, right? So what do we want in an uninformative prior? One thing is we want to be unbiasing, so we don't like this, right? Now if we get some data here, the best fit is here, maybe we don't like to just have the best fit, but our ensemble is going to be way over here, and that's bad. We would also like this model to be reparameterization invariant, or this prior to be reparameterization invariant. And I'm just going to write down what Jeffrey said the answer to these problems is, or what he proposed. New color here. So Jeffrey's prior. It's his prior, but his name is Jeffries. This threw me off a lot for Googling. And Pj of theta is just the square root of the determinant of the Fisher information. A proportional sign here. where this is the metric that we've been talking about all along. So G is the Fisher information. And what that means is that Jeffreys prior is flat in this space. Let me draw that. And so is this familiar from general relativity, perhaps? So in general relativity, if you want to convert between coordinate distances to proper distances, you use the metric. If you want to convert from coordinate volumes to proper volumes, you use the square root of the determinant of the metric. And one way to think about that is that the square root of the metric measures length. And if I want to take the determinant, that's the product of all the lengths squared. So if I want to turn it into a volume, I just need to take the square root. So Jeffreys prior fills this out. I also want to draw it in this space. Sorry, I skipped one thing. So here's my best fit here, right? So Jeffreys prior, well, it's a little bit hard to draw here. But the first thing to note is that it actually knows about T1 and T2. So here's T1. Here's T2. I can put these on here. So here's 1 over T2, 1 over T1, right? And Jeffreys prior says that you should put weight on parameter combinations that are sort of this order, right? Because it's telling you that you should choose your parameters such that they're actually changing the observables. Without being too precise, Jeffreys prior looks something like this. It has some weight everywhere, but it's concentrated in the regime of parameters K1 and K2, where changing the parameters is actually going to make a change to the model. Sorry, so never mind. This is just to say that G is the Fisher information. Okay. Sorry, let me actually also draw Jeffreys prior here. So the claim is that this sort of sweeps out the range of possible behaviors we can get, right? So it's sweeping out the total area of different sums of two exponentials that I can get in this as measured by these two data points. Okay. So Jeffreys prior is quite a big improvement over the two flat priors I discussed, but I now that I've set it up, I want to argue that it still has some problems. And in particular, this is measuring the area of this, but imagine that I bring T1 and T2 close together. If T1 and T2 were at the same point, then this would just be a line, right? And as I move T1 and T2 close to each other, this model manifold is going to shrink, right, and become very hyperribbon-like, with one very long direction and one very thin direction. And Jeffreys prior somehow doesn't know about this, right? So Jeffreys prior says you should always measure the area of this. And there's some sense in which that's a strange thing to do, right? So if I ask you how big this piece of paper is, you should be telling me the area. But Jeffreys prior says, well, no, it has some width, and you should be measuring the volume. And so this is kind of strange. For a single T1, Jeffreys prior is actually going to be measuring linear distance, right? Okay, maybe it's a little strange because the Fisher information will have zeros then. But if I just have a single parameter, then Jeffreys prior is going to be measuring linear distance, but with two, it's going to be measuring area. So Jeffreys prior does have dependence on the data. So depends not just on theta, but on ti. Depends on ti. But it doesn't depend on m. And in particular, I would argue that as these get very close to each other, you'd really get exactly the same results if you just had a single exponential, right? But Jeffreys prior would weight these very differently, right? So if, as these get very close to each other, you're really just, your model is giving you a number between 0 and 1, and you get no new information by having them separate, and yet Jeffreys prior is going to weight them very differently, right? Because as it's drawn here, these parts here are very thin, this part in the middle is very thick, and so actually, Jeffreys prior will always tell you to move towards the center of this manifold, and that's biasing in a subtler but still real way. Does that make sense? So somehow your prior now makes very different predictions for models that are different in the number of parameters that they have, but which make essentially equivalent predictions. Yeah. No, so Jeffreys prior is always the dimensionality of the parameter space, right? So, okay, it's a strange thing if you have more parameters than data points, but as long as you have the same number or more data points, this isn't an issue. So I was careful not to include an A prefactor here, for example. So if I had another parameter for the prefactor here, then the total volume would not be finite. But this is actually not such a bad problem in the sense that in that case, so there's some parameter evaporation, but the first data point will correct it. Right, so the first data point now exponentially suppresses all the things that have A's that are wrong. So, okay, I guess mostly I'd like to sweep this under the rug, but say that in typical models, if there are extended directions, there aren't many. But there's lots of directions like this that are finite.
In the end, I guess the issue of parameter evaporation is whether your classifier depends sensitively on your arbitrary choice between maps.
In some sense, yeah, it's exactly that. It's as you take your parameters to infinity, do they still have finite cost? And if they do, they go together, right? If they do, then this model manifold has to be finite, right? Because cost here is just distance. And if they don't, then Jeffreys prior will have this infinity in it, but not in such a problematic way. That's okay. Okay, so this is what I want to say about Jeffreys prior, and now I want to introduce the concept of the reference prior, and the idea is to make this concept of an uninformative prior more precise. So these are sort of principles, but they don't tell you how to compare two priors and say which one is better, right? And the idea of the reference prior due to Bernardo. Is the following. So if I give you a P of theta, that really defines P of x. So right, so my choice of P of theta doesn't just define this probability distribution, it also defines this, and it defines joint probability distributions and conditional probability distributions. And what they said you should do is treat the mutual information between the parameters and the data as a functional of this P of theta. right? And then they want you to optimize this. So they want to choose a p of theta. So choose p star of theta. The reference prior, which is going to maximize the mutual information between parameters and data. Okay, and there's a few ways to understand this. The first one I'm going to tell you is to think of it as an optimist prior. So mutual information between x and theta, I can write as the entropy in theta minus the entropy in theta after I get my data. And this is saying, let's choose a prior such that if it were true, I would learn as much as possible from my experiment, right? The other way we can write this prior is as an expectation value of f of theta, where f of theta is the Kullback-Leibler divergence between the probability distribution on x after I've conditioned on theta and the total distribution. And one way you can think about this is that f of theta is really quantifying how bad the parameter value theta is, or if theta were the true distribution, this is how bad a job your distribution p of x is at fitting it, right? So this is telling you how bad your estimate is of the true distribution. Yeah, so f of theta is a functional of p of theta, but so f of theta depends on this p of x, right? So this is your expected data, not the data that you've actually received. So this is all before you've actually seen data, right? So, okay, so this one I think is the optimist interpretation. Now I'm going to derive the pessimist interpretation, which is that you want to minimize the worst case f of theta. So now you're assuming that the world is trying to trick you, and you want to minimize the worst case f of theta. So if you want to maximize the best case f of theta, that's easy, right? You just put a delta function somewhere. But it turns out that optimizing the worst case or minimizing the worst case is the same as maximizing the average case. And I guess I'm going to show you how what happens when you maximize this, and maybe the result will be believable. Okay. Okay, so if I want to find the optimal of this, I can take a functional derivative. So d by dp of theta. And I want to take the following functional derivative. Integral d theta p theta f of theta plus, I need to enforce that the integral over the probability distribution is 1. And all of this equals 0, right? Maybe I will not go through the algebra here, but what you find that f of theta equals a constant is the solution here. Is the mutual information. And so maybe this is getting at your question. So if I look at this solution, I could move my p of theta around and move some of it from one area to another. And that would decrease f in some places, right? So I'd now be closer to that model, but I'd have to increase it somewhere else. And so it turns out that when you optimize this, you also minimize the worst case scenario. And the optimal occurs when f of theta is a constant everywhere. Is this okay? It is a minimax thing. So you maximize the expectation value of f of theta. And by doing that, you set them all to be equal to each other. And this also minimizes the worst case scenario. Yeah, so I have not shown that. I agree. Okay, so this will turn out to have complications, but in the meantime, what I want to show you is that as I take the limit that m goes to infinity, when I do this minimization, I'm going to recover Jeffrey's prior. Okay, so this derivation is a little bit suspicious, and in fact, people argue about this still. So you can still write papers where you show that that optimizing that the reference prior as m goes to infinity approaches Jeffrey's prior, and I'll try and show you where these assumptions are. But for this model that I've shown you, and for most sort of generic models, all of the assumptions that I'm going to be telling you are sort of true. Okay, so as m goes to infinity, let me first define the maximum likelihood estimator. This is a function of the data, and it's the parameter set theta, which would have been most likely to have produced this x. So it's the theta which has the maximum likelihood. So I haven't told you how you calculate this from x, but if I give you an x, this is well defined, right? The Kramer-Rao bound says that as m goes to infinity, the probability of theta hat given theta goes like g to the 1/2 right, so let me just say this in words. As m goes to infinity, I'm sorry. As m goes to infinity, the probability of the maximum likelihood estimator given the actual parameter values is going to approach a Gaussian whose width is getting smaller and smaller as m increases, and it's going to have this form, right? So as my data set gets larger and larger, eventually I'm going to reach the true values, and my error bars are going to be Gaussian distributed around that with standard deviation that shrinks as m gets large. Absolutely, yes. Yes, this is G mu nu. Okay, the other thing I need to tell you is that in this limit, theta hat is a sufficient statistic of x. And what that means is if I tell you theta hat, you actually learn nothing more about theta if I tell you all of x. And so to give you an example of what that means, in this particular problem, if I tell you that the maximum likelihood estimator is here, you actually learn nothing by hearing where all the individual points were, right? That the maximum likelihood estimate is going to be Gaussian distributed around the real one, and the noise is going to be Gaussian distributed around that, and telling you the actual data points tells you nothing more. And what this means is that this is well approximated, or as it actually becomes a sufficient statistic, this is the same as DKL P of theta hat given theta P of theta hat. Is this okay? Okay. There's one more thing which I need to tell you about, which is that in this limit, P of theta hat equals P of theta. And this is a slightly rocky assumption, but can anyone try and justify it for me? Okay, so let me try to convince you. So as m gets very large, this model is only going to be confusable for its very nearby neighbors, right? And if we're willing to assume that the prior is continuous, then the prior on the nearby neighbors that this model is sort of sharing its probability distribution with, they're going to be the same, right? And so for purposes exactly. That's
just convolving with a delta function.
Exactly. So I'm convolving with or at least with a function that's much more sharply peaked than any structure in the prior. So as m goes to infinity, this is roughly true. And actually, this is, I think is the most questionable assumption here, and the one that people still fight about. And I don't have an opinion on this fight. But if you're willing to assume that it's a continuous pair, then this is true. And what you find then is that this I'm going to write as constant plus log determinant g to the 1/2 minus log p of theta, right? And what this means is that p star is proportional, p star of theta is proportional to g to the 1/2. Is this okay? Okay. So hopefully this made some sense. If not, I think it's maybe a believable answer, right? So as m gets very large, if I want to choose my prior somewhere in this space such that I can gain the most information from a data point, roughly what I want to do is spread out in this space as much as possible, because the data that I'm going to get is going to put me in a little circle somewhere on this space. And sort of the more widely distributed I am in here, the more circles I can place in sort of a hand-wavy sense. And this is an algebra that sort of justifies that. But there's a few assumptions in here that don't seem likely to be true in the limit where m doesn't go to infinity. And to give you some intuition for that, right? If my data is, if my error bars are very large compared to the width of this manifold, then I'm actually not really learning anything about this direction, right? When I get my data that's telling me something about where I am in this direction, but maximizing the mutual information should roughly ignore the width in this direction, right? Because I don't learn anything about where I am in that direction anyway. Does that make sense? Okay, so I'm actually just going to plot what these are.
So you're saying if M could be so large that indeed you can actually tell where you are in this direction, or it could be only large enough to tell you where you are in this direction, but not in this direction.
Absolutely. So if M is large enough, I really could extract, even as T1 goes to T2, I could extract 2 exponentials from this, right?
But if we hold M large but finite and take T1 to T2 limit holding M fixed,
Yeah.
then we'll recover the Jeffreys prior as if we had just had one.
Yes, that's the hope. Yes, we'd like to see this happening, yes. Okay, as an introduction to this M small limit, I'm actually just going to plot the results for a coin flip. Okay, so X now is going to be either a 0 or a 1. P of 1 is going to be theta. P of 0 is going to be 1 minus theta. And well, it's a simple exercise to calculate Jeffreys prior for this, but let me just draw it down here. So here's theta here. And Jeffreys prior looks something like this. So it actually diverges weakly at the edges here. And if you believe this calculation, as M goes to infinity, this is the prior. And this is f of theta. So the distance between all models is equal. But now let me show you what happens if I just have a single coin flip. So here's M equals. And then you can numerically optimize this, and what you find is that all of the weight is going to be on the edges. Here's P of theta. And when I plot f of theta, it looks something like this. Where this is the mutual information. So firstly, why is 2 delta functions, why is that the prior that optimizes the mutual information between theta and x? Yeah, so this is true, but it's a little bit circular, right? Yeah, so I guess what I'd say is if I chose this prior, I'll get exactly 1 bit. And that's really the maximum I could possibly get from this, right? I'm going to flip a coin once. The entropy of the data is just 1 bit. I can't possibly learn more than 1 bit from this experiment, right? And you can convince yourself that this is a unique optimum, right? If I put some weight in the middle, that's not going to help me, right? So where did this argument go wrong, right? So at the beginning, I was arguing that the reference prior, is it still up here? Yeah. That f of theta has to be a constant here. Well, we forgot another constraint, which is that p of theta has to be greater than or equal to 0. So p of theta can't be an arbitrary function, right? It has to be positive. And as a result, this is not quite the whole picture, right? Because my this functional derivative that I took, there's other solutions possible. And in fact, f of theta equals constant equals the mutual information, or f of theta is less than the mutual information and p of theta equals 0. So these are the two possible ways that this prior can be satisfied. And as m goes to infinity, this constraint is never activated in some sense. But for finite m, this prior is typically going to be a finite set of delta functions. So I'll just draw one more of these so you can see the pattern. So if I have 12 coin flips, I still have my two delta functions on the edges. But now I'm going to have some delta functions on the interior also. And when I plot f of theta, here's the mutual information. It's going to look something like this. Okay. The things that I'd like you to take from this for this more complicated summing exponential picture is that this prior tends to be discrete. So as m goes to infinity, it would like to sort of spread itself out continuously. But for finite m, it's going to really like to sit on these boundaries. And it's going to be discrete even on the interior. OK. So this is most of what I want to say, but I want to draw our numerical results for the sum of exponentials. And actually, why don't I draw them on here? OK, so the error bars also belong on here. So when my error bars are large, right? This prior is actually just going to be two zero-parameter models. One here and one here. And I think this actually makes sense. So if your error bars are huge, basically what you want to see in this experiment is whether your radioactive elements are decaying faster or slower than T1 and T2, right? As the error bars get smaller, this other zero-dimensional model gets some weight. And I also start to pick up weight on these edges here. And as Mark has been talking about, these edges really correspond to simpler models. And actually, you need to get the error bars to be quite small. So quite a bit smaller than the width of this manifold before you start getting points in the interior. So that's what I want to say about priors. And so I'm not sure whether I believe that this is the reason to think that you should use a simpler model. I still like the idea that it's really an aesthetic reason, that a simpler model you can look at and understand. But I do think it's pleasing that this prior that you can really motivate on information theoretic grounds does tell you that you should be using a simpler model. So I'm about to make quite the shift in gears. Any more questions on this? Yeah.
So the discreteness you don't consider a bad thing. It's a good thing. It's basically saying you made your life more complicated than it needed to be. You should not consider that the coin is probabilistic. You should just assume that it's deterministic, and you're just trying to establish whether it's always heads or always tails, and not pretend that it's probabilistic. Because you'll never know from your experiment if it was probabilistic, so just forget about that possibility.
Exactly. Yeah, so I mean, an experiment that you're only going to repeat once, that's the flip of a single coin, is very strange, right? So this is something like the probability that a Democrat will win the 2020 election, right? This is, maybe it's a probability, but it's a singular event, and maybe it makes sense not to talk about a distribution of thetas, but just to say we want to know the probability of theta equals 0 or 1. And if I'm going to repeat the same experiment multiple times, then I can start talking about thetas in between that. But if you don't have enough data that you can distinguish them anyways, maybe it's a silly question. So there are times when you actually want to know the parameter values. And if that's what you're trying to do, this is obviously a silly prior, right? So if you use this prior and you take some data and it puts more weight here, right? You should not conclude that your elements decayed infinitely quickly. And so if that's what you're trying to get out of it, this is not a good prior to use. But if what you're trying to do is understand what the data likely was, this will give you more information.
I mean, in some sense, that's a case where actually you have a ton of other information, which is all the experiments that have ever been done on these elements. And so obviously you're going to build that information into your model and into your prior. Sure. And the story you're telling now is kind of not knowing. You're just making the simplest model you can for the given experiment you have. Yeah. Right? Yes. If somebody has already done 1,000 experiments on the same thing, obviously you're going to incorporate that in your prior, and that's a very different story.
Absolutely. So this is for uninformative priors, which is to be distinguished from sort of the everyday use of prior knowledge about the world. Yeah. So this is I would claim that you could think about, if somebody tells you what those experiments are, you'd still want to have a prior to start with, right? And this is the way to choose that. Okay. Start erasing this. This next half, or the last third of this, I really want to be an introduction to tomorrow's lecture, and to get people on the same page about what I'm thinking about. So let me actually write up a hypothetical experiment here. So I have a little loop of DNA here, which I think in the article I sent out, they actually used RNA. And with some fancy chemistry, this DNA has been affixed to a little glass bead. And then they're going to shine a laser at it. And the laser is going to be refracted. And because the laser light is refracted like this, it's going to exert a force on the DNA molecule. And with some clever techniques, you can actually measure the position of this and how much force is being exerted and try and control it. And the general question that I'm going to be asking for the next days, so let me denote X now to be the microscopic configuration here. And in the information geometry framework, this microstate is going to play the role that our data played when we were talking about fitting problems. This is going to be phi of x, so the actual location of the glass bead, which is some function of the microstate here. Sorry? The microstate is the whole configuration of the RNA molecule and all the water molecules. So it's really the microstate in the thermodynamic sense. And I'm going to be actually, with this laser experiment, it's a little strange to keep it at fixed force, but that's going to be the easier one to think about. And I want to think about keeping this at fixed force and allowing this microstate and by extension, the extension here to fluctuate back and forth as that happens, right? And what I want to ask is, so here F is going to be lambda. How much dissipation is going to be associated with a protocol lambda of t? How much entropy is going to be produced during a protocol lambda of t? And to give you sort of an overview of where this is going, today I'm going to first do a very quick overview of the Jarzynski equality, which gives an exact equality for this. Then tomorrow I'm going to take the linear response limit. So today I'm also going to derive the fluctuation dissipation theorem, which is maybe the most important result from the linear regime of this. And then tomorrow I'm going to use other linear regimes to motivate some geometric bounds on how much dissipation it's going to take to move this particle around. Okay. So what we want to show, I'm going to put the result up. This is the Jarzynski equality that e to the minus beta times the work. The expectation value of this, as I do this along any arbitrary protocol, not necessarily in the slow limit, is equal to e to the minus beta delta f, the change in free energy. Okay, and actually, I just want to start by calculating this, this left-hand side, and hopefully we're going to get this to come out. I'm going to follow assumptions that are rather close to the original Jarzynski paper, or a similar derivation. So the assumptions are, first, that we're going to have a closed system. So you can think about this experiment all taking place in a big water bath, but a water bath that's not allowed to talk to its environment. So closed system. No, so I want you to think about the whole system, this X, as being a very large water bath. Yeah, so a closed system that I've taken from thermodynamic equilibrium. So it was attached to a heat bath. I let it come to equilibrium, and then I detached the heat bath. And I'm hoping that if you take this water bath to be large, that you'll agree that this is really not so different from keeping it attached to a thermal reservoir. But it makes the derivation much easier.
So it's large enough that there's no like dual heating of the bath I mean, if it's really closed and I inject a lot of energy, then of course it'll heat up.
I see. Yeah, that's true. So we want to be in the limit that that beta is a constant during this experiment. Yeah. So eventually you can think about including the heat bath as part of this system, and that'll make it precise. Yeah. Okay. And we're going to think about deterministic lambdas for now. So we're going to be given a lambda of t. And because this is a closed system, actually if I give you x naught, this specifies x at all later times. Right? So x naught goes to x of t. And eventually to x final, some final configuration. And in particular, if this system is really Hamiltonian, if it's undergoing Hamiltonian dynamics, then this Jacobian has to be equal to 1, right? So is this okay? So this is true of any system that's undergoing Hamiltonian dynamics. And let me see, I think this is all of the assumptions that I need to write down. Okay, so this is what we want to calculate. And this is going to be an integral over dx naught, so an integral over initial configurations, p of x naught. And now, if this is deterministic, then the amount of work that I do on the system as I undergo one of these, as I undergo this protocol, is also going to be deterministic, right? And it's just a function of the initial state. Like this. Yeah? So now I want to write this as a usual Boltzmann distribution. And the assumption here is that I'm actually, I'm going to start with the system in contact with a heat bath, and I'm going to wait a long time, and then I'm going to disconnect it. So this is 1 over z naught. So now I have P of x naught. Okay, so now I want to use that this is a closed system one more time to write E final as a function of x final as E naught of x naught plus the work done on x naught. Is this okay? Okay, so there's one more thing I need to do, which is change coordinates from x naught to xf. So this is going to have a Jacobian dxf dx naught. I'm sorry, not dxf. dxf, right? And now this whole product here I can replace with e to the minus right? And this is just a rewriting of the final partition function, right? So this equals z final over z naught, and this is just minus beta delta f. So that's what we initially wanted to prove. This is a general result, so this really doesn't depend on any assumptions of smallness of lambda of t. In fact, I never really used lambda of t here, right? But for the rest of today's lecture and tomorrow's lecture, we're just going to be making some we're going to be making some smallness assumptions about lambda of t and about the work. And to motivate that, I actually want to expand this out. Yeah.
Did you also just prove that at the end of the protocol,
No. Yeah. So okay. This is actually quite confusing. It looks as though I've shown here that at the end it's in thermodynamic equilibrium, but this is not the probability distribution at the end. I mean, you know, this is this, right? And it looks like an equilibrium distribution, but it's not.
so then what do we mean by F final? It's not
Yeah, so F final is the free energy of the equilibrium distribution at the end, which it's not in. Yes. It could be in it if we waited a long time, right? If we kept the parameters fixed and waited a very long time, presumably it would reach something like thermodynamic equilibrium. By ergodicity, yeah. But we don't need to wait that long, and this would still be true.
Wait, but I'm still slightly confused. So, but So we have
temperature hasn't changed.
To change the temperature.
Yes.
So how could is the free energy depending on more than just
the actual temperature? You said this is all dependent on temperature. There's no restriction on that.
No restriction on lambda, yeah.
If you do this and wait a long time, eventually the temperature. No, he's assuming it's big enough.
I want a big enough bath that there's no Joule heating, yeah.
So what is the free energy depending on that it could change if the temperature didn't change?
A lambda. So as I move this part, so as I change the force, I'm going to change the free energy, right?
Oh, that's the other external. Oh, that's the external parameter. Oh, I see. So the free energy is a function of beta and delta.
Yes. Oh, I'm sorry. And this is yes.
So if you did a cycle, let's say, then delta F would be 0. Okay.
Absolutely. So if I do a cycle, then delta F is 0, but it's not necessarily true that I haven't done work. And this is going to be true regardless. So actually, what I'm going to be doing today is considering, small changes in lambda that eventually come back to the same point. Okay, so the right-hand side does not, so if I'm willing to assume that lambda is deterministic, so this lambda of t is deterministic, the right-hand side here doesn't need expectation values, right? The free energy at the end is a well-defined function, and this is the equilibrium free energy. But this is confusing, and we need to think about how to expand it. So the first thing I'll just state is that expectation value of e to the minus x, this is larger than or equal to e to the minus x. And if we take the log of both sides of this, what this means is that the work is greater than or equal to the change in the free energy. So in some sense, we've actually derived the second law here, right? This is one formulation of the second law. And it's usually sort of motivated on principles of entropy increasing. But here, really, by assuming that volume and phase space was preserved, we've sort of proven the second law. And I think this is very counterintuitive, right? This sort of seems like the assumption that entropy is staying fixed, but not quite. And actually, you can use it to show the second law. The next thing I want to do is actually expand this, and eventually we're going to get to cumulants. But to motivate that, I want to actually just Taylor expand this. This is going to be the expectation value of 1 minus beta work plus 1/2 beta squared work squared minus, right, like this. And now if I take the log of e to the minus beta work, and expand this out, assuming that all of these terms are going to be small, what I'm going to get is but then I need to include the next term in the log. So this is going to be minus, and then I need this whole term squared. And this term kind of lines up with this in that they're both order beta squared. Yes. Thank you. And then there's going to be confusing third order terms like this. And then I need another term which is now only going to contribute here and farther. and so on and so forth. And this is going to define the cumulants so this is the second cumulant here, work squared minus expectation value of work squared. If I were to do all the terms here, I'd get the third cumulant. And I can keep adding terms like this. How am I for time? OK, I do still have a little bit more time. And the idea of linear response, so all the things that I'm going to be talking about, I guess, for the next 8 minutes, but also for tomorrow, are just going to be using these first two terms. And actually, these first two terms were basically nicely understood before the Jarzynski equality. So now that we have the Jarzynski equality, I think this is a very nice way of thinking about these, but you can derive these first two terms, these linear response-like terms, without them. OK. In the next 5 minutes, I'm going to derive the fluctuation dissipation theorem for you. And this is a slightly non-standard derivation, but it makes use of the Jarzynski equality, and it's going to be in a similar theme to what we're going to be doing tomorrow. And the idea is, let's imagine that I have some protocol that's sort of only non-zero in some finite range. So here's lambda of t here. Here's time here. And it's going to be 0 for a while, and then it's going to do some who knows what for a little while, and then it's going to go back to 0. And I want to calculate how much entropy this is going to produce on average. And now let me plot a particular x. Sorry, this is phi 1. So on one realization, I have something like this. If I do another realization, does something like this. And if I average this, presumably, as long as this is small, I'm going to track it, but just barely. And maybe with some lag. So maybe I'll miss some bits. And eventually, I'll go back to 0. This is phi. And there's two things that I want to relate here. So one is the susceptibility. So if I Fourier transform this, this is going to be related by this susceptibility to lambda omega. So I'm going to define lambda omega a little more carefully in a second. And the other thing that I want to define is the correlation function, or the spectrum of fluctuations in this space. And that's with S omega is the expectation value. Sorry. So this is what we're going to try and do, is relate these. OK, and let me first write down the work. So the work that's done during this protocol is going to be integral dt d lambda dt times phi of t. Is this okay? Actually, I think in this particular setup that I've written down, it's actually going to be d lambda dt or d phi dt times lambda, but in a simpler setup, it would be this, and they're going to end up being equivalent. And I want to define lambda of t to be 1 over root 2 pi and I want to with an analogous definition for phi tilde of omega. And in this, the expectation value for the work, or sorry, the work here is going to be written as d omega minus I omega lambda tilde omega times x tilde omega. Is this okay? The expectation value for the work is going to be given by d omega minus I omega lambda tilde omega. And the expectation value for x tilde of omega is the only thing that fluctuates here, right? So lambda tilde is by assumption a deterministic process. And so I'm actually going to replace it by this. This should have a minus sign here. Now this function chi is Hermitian. And what that means is this minus I omega is going to cancel the real part, but it's going to leave the imaginary part. So I'm going to write this as integral d omega times omega times the imaginary part chi of omega times lambda omega squared. Yeah? Okay, so omega squared, I can still use these for both of my omegas. The omega prime, lambda omega prime, and now I have x tilde of minus omega like this. And now I'm going to replace this with s omega. Okay, I've forgotten an omega squared, right? This here. I'm sorry. This should have times omega prime. But these are correlated only if omega equals omega prime. Okay, my apologies here. And so this is going to be omega squared s of omega. And now we want this to be true whatever our lambda is. And what this means is using the Jarzynski equality here. So the change in free energy is 0, so I want beta omega to equal 1/2 beta squared omega squared. And this means that beta omega times the imaginary part of chi equals 1/2 beta squared omega squared s of omega, and this is, let me write this out properly. KBT over omega, s of omega. So this relates this spectrum of fluctuations. This makes no sense, right? I'm sorry. Imaginary part of chi of omega. Okay, so this relates the spectrum of fluctuations to the susceptibility as a function of frequency. And I could stop. Questions? Yeah, so the Jarzynski equality relates these two. So I've calculated omega squared here, or the second cumulant of the work, and the first cumulant of the work. And the Jarzynski equality says that I can relate them. Yes. Yes.